Good morning. Now these videos we are going to start for graph theory. So maximum students demanded graph theory lectures. What we are going to do in next 3-4 videos, very basic things of graph theory. So first in this video I will just define basic terms of graph theory. Let's see one by one. What is a graph? The basic terms which we are going to see, I'll just note down here and we will see one by one. So, what is a graph? What is a simple graph? Then, adjacent vertices. Next, adjacent edges. Then, we have isolated vertex. Next, we'll define degree of vertex. Next, even and odd vertex, null vertex, complete graph, and lastly regular graph. So let's see these terms. So first thing, let's define what is a graph. Now in graph, first of all, we are going to have a set V. Let's say elements of V are V1, V2, Vn, and we will have a set E which is two element subset. So I will denote it by say V1, V2, V1, V3, V2, V4, etc. I'll give example and then we will define it properly. When suppose I have V1, V2, V3, V4 and our E is say V1, V2, V2, V4, V3, V4. This is a graph. What we are going to do here? We have 4 vertices. Let's have V1, V2, V3, V4. These are elements of V. Now what we have here? V1, V2. So we have a line between V1 and V2 which we are going to call as an edge. Next we have V2, V4 and then we have V3, V4. So you can see this is a graph. So in general, how we will define? V is a set of elements, say V1, V2, Vn, and E is, in general, I will write Vi, Vj for some Ij. Means it's not we have all combinations of Vi, Vj. Then this V together with E is called as a graph. This is a graph. So analytic definition is this. Geometrically we represent it in this way. So what is graph? Graph consists of first of all a set V with elements V1, V2, Vn. E is Vi, Vj. It's not ordered pair. That is the most important thing. You may have V1, V2. You may have V2, V1. So this is Vi, Vj for some Ij. Then V together with E is called a graph. That is our first definition of graph. And in this itself I will tell you, V we call as set of vertices is called as set of edges because this every pair, say V1, V2, we are going to call it as an edge. This is another edge, this is another edge, and usually we denote edges by E1, E2, E3, etc. So this is the meaning of graph. Now let's go for next. Simple graph. Simple graph means now, as I said, our edge set is Vi, Vj. I am not given any restriction on I and j, so I may add vi because currently no restriction on I and j. But if a graph is such that there is no edge of the type vi, for example, now let's have this graph V1, V2, V3. Now you know what is graph. So in this graph, what are our edges? V1, V2, V2, V3, V2, V4, V4, V5. If I have V1, V1 also, V1, V1 also means that will be shown in this way. This kind of graph is not a simple graph. So simple graph means a graph where we don't have edge of the type VI, VI. That is called as simple graph. That is the meaning of simple graph. Now before I proceed for next, I will just tell you this graph, which obviously graph, so we denote it by G, and this says usually instead of saying V, we write as VG, that is vertex set of graph G, and this we denote as EG, that is edge set of graph G. So this is what I explain you, what is a graph, what is a simple graph. Next we'll go for adjacent vertices. Adjacent vertices are very simple. Again, look at this graph. You can see V1, V2 is an edge in this graph. We are talking about simple. So this is not there. So if we consider this graph, you can see V1 and V2. This edge is there. So we say V1 and V2 are adjacent vertices. V1 and V2 are adjacent vertices, means in general we say Vi and Vj are adjacent vertices if Vi Vj belongs to Eg, that's its edge set G, means Vi Vj is an edge. So you can see here example V1 and V2 are adjacent, but V1 and V3 are not adjacent. V3 and V5 are also not adjacent. V2 and V4 are adjacent. That is the meaning of adjacent vertices. Next I will tell you adjacent edges. It has again similar meaning. First I will show you here, then I will define it. Again you can see, look at this edge. If I denote these edges by E1, E2, E3, E4, I will say E1 and E2 are adjacent, but E2 and E4 are not adjacent. Now you can understand the definition. E1 and E2 are adjacent. How come? What is E1? E1 is V1, V2. What is E2? It is V2, V3. So these edges we call as adjacent. Means how will I define now? Two edges, if one is Vi Vj and other one is Vj Vk, then these two edges are called as adjacent vertices. You understood the meaning now? Sorry, adjacent edges. This is okay. So once again I will tell you adjacent vertices means if there is edge between Vi and Vj, Vi Vj are called as adjacent vertices, and edge of the type, one edge is Vi Vj, other is Vj Vk, then these two edges are called as adjacent edges. Now next is isolated vertex. What is isolated vertex? Again in this graph, say I have vertex V6. How is this V6? You can see V6 is not adjacent to any of these vertices. V6 is not adjacent to any other vertices. Then we say V6, we will call it as isolated vertex. Now we will define any vertex Vi is called as an isolated vertex if there does not exist any Vi Vj belonging to edge set of G. There is no edge Vi to Vj. Then Vi we are going to call as an isolated vertex. So here it is V6. Next I will go for degree of vertex. What is the meaning of degree of vertex? Again have this graph as an example. We can see, I will say here, degree of V1 is 1 because from V1 we have only one edge. There is only one edge from V1, or you can say 2V1, whatever. only one edge incident on V1. So I will say degree of V1 is 1. For V2, you can see E1 is there, E2 is there and E3 is also there. So I will say here degree of V2 is 3. Now you can tell me degree of V4 is 2, degree of V3 is 1, degree of V5 is also 1, and what is degree of V6? Degree of V6 is 0. So degree of a vertex means number of edges incident on that vertex. That is degree of a vertex. For even and odd vertex, it's very simple. The vertex whose degree is even, that is called as even vertex. The vertex whose degree is odd is called as an odd vertex. So you can check here again. V1. V1 is an odd vertex because degree is 1. V2 degree is 3. So it is again odd vertex. V4 its degree is 2. So it is an even vertex. And a vertex whose degree is 0, that is called as an null vertex. So null vertex is same as isolated vertex. So that is your even and odd vertex and null vertex. So these are the basic things what you need in graph theory. And now next we will see what is called as complete graph and what is called as a regular graph. Now for a complete graph, again I'll give you some example. Let me wipe out now these things. So complete graph, first let's have some graph on 4 vertices. These are 4 vertices. This is one graph on 4 vertices. Now you can see here, if I call this V1, V2, V3, V4, what you can see, V1 is not adjacent to V2. We are going to talk about the graph in which every vertex is adjacent to rest all vertices. Means V1 is adjacent to V2, V3, V4 all. Look at this. V2 must be adjacent to all. V1 is already there. V3, V4. V3 must be adjacent to all. V1, V2, V4. We see V4 is adjacent to all. So this type of graph we call as a complete graph. So what is the meaning of complete graph? How will define it? Complete graph on n vertices is a graph in which every vertex is adjacent to rest all vertices. That is the complete graph. You can try one more example. Complete graph on 5 vertices. What kind of graph it will be? See, every vertex must be adjacent to rest all. Start with another. Every vertex must be adjacent to rest all. And this is complete graph on 5 vertices. We denote it by K5. This is K4. So in general, Kn. This is complete graph on n vertices. Next, the last term which I wrote here, that is regular graph. Regular graph is, in simple words, I will define a graph in which every vertex has same degree. Let's have this. This is a graph. You can see every vertex has degree 2. If I have this, it is a graph in which every vertex has degree 3. So the graph where every vertex has same degree is a regular graph. So you can see every complete graph is regular. Every complete graph is regular because whatever vertices are there, if it has n vertices, every vertex is adjacent to rest all n minus 1 vertices. So obviously degree will be n minus 1. That is for every vertex. So this is n minus 1 regular graph. So you can say every complete graph is regular. But every regular is obviously not complete. So here I have given you the example where it is regular but not complete. This is, we write it as 2 regular. 2 regular means a graph is regular where degree of each vertex is 2. So these were some basic terms of graph theory, and now we will go for next, what is called as an isomorphism. Isomorphism of graph. Now again, before giving you the definition, I will try to explain the concept. Just recollect, we had done isomorphism of groups. It's a similar thing, isomorphism of graph. Let's have an example. I will try to explain the concept. Say, this is the graph 1, 2, 3, 4. And now, have a look on this graph. A, B, C, D. It's very good example, but understand concept of isomorphism from this, and it won't take any time for you to understand. Actually, these graphs are one and the same. This I just tilde it. I just sketched in this way. So if you just turn your notebook, it will look like this. That's it. One more thing. Here I have given 1, 2, 3, 4. Here I have given the name A, B, C, D. So forget isomorphism, or for a minute forget mathematics. In general, if these two sketches are in front of you, what you will say? They are same. Only instead of 1, I have written A. Means 1 is same as A, 2 is same as B, 3 is same as C, etc. Let's put this mathematically, and that is the isomorphism. So these two graphs are isomorphism. Now I am saying isomorphism, so mathematically how will say? Just now you said 1 is same as A, 2 is same as B. In maths we won't say 1 is same as A. So what we are going to do, this graph, if I denote this by G, this I denote by G dash. For G, my vertex says is 1, 2, 3, 4, and for G dash, our vertex set is A, B, C, D, and we will say the graphs are isomorphic. The first thing we have, there must exist F from vertex set of G to vertex set of G dash such that F is bijective. Now please recollect, we have already seen what is a bijective function. So first of all, it should be a function and it must be a bijective, that is 1, 1 and onto. If you want, I will just recollect what is a function. Function means function from A to B. Every element must be related to one and only one element. Means it should not be this way. Means it is related to this as well as this. It is not a function. That was our first condition. And every element must be related. So we have an element here which is not related to this. Again, that cannot be a function. Then 1, 1. 1, 1 means if I have this kind of function, look at this. If I have this, it is a function, because as I said, function from A to B. So this element should not be related to 2, but there was no condition on B. We can have 2 pre-images for element of A. It is a function, but in this case it is not 1, 1. 1, 1 means every element of B must have only one pre-image, that is 1, 1 and on 2. If the function is this way, it is a function, because again for function, there is no condition on B. I said every element of A must be related. No condition on B. But if it is this, it is not onto. What onto says? Every element of B must have pre-image here. That is 1, 1 and onto, or what we say, injective and surjective. And that is called as bijective function. So to define isomorphism, first thing, there must be F from, it is a function from vertex set of G to vertex set of G dash. How is that? F must be biject. Secondly, it is not just like there must be 1, 1 function from set of vertices. See properly, if I have this, here again you can see, come on, what can we see? There is one and bijective function for vertex set, both vertex set, but you can see it is not isomorphic. These graphs are not same. So what should be my second condition? My second condition says UV belongs to EG implies FUFV belongs to EG dash. What is the meaning of this? See properly. Pick up any two elements here. 1, 2, 2. 1, 2 is an edge here for graph G. What is our f of 1? F of 1 is A. F of 2 is B. So if 1, 2 is an edge for G, AB must be an edge for G dash. Means whenever UV is an edge in G, FUFV must be an edge in G dash. That is the very important condition of isomorphism. And now you can get proper definition of isomorphism. I will say G and G dash, these two graphs are called isomorphic if there exists a function f from Vg to Vg dash, that is vertex set of G to vertex set of G dash, such that first condition f must be bijective, and second condition whenever UV is an edge in G, then FU must be edge in G dash. That is the simple meaning of isomorphic function. Just go through for a second. Now I will give you one simple example, and the question may be find whether the graphs are isomorphic or not. If I give you, this is say my G and this is my G dash. Let me have this as U1, U2, U3, U4, U5, and let's have V1, V2, V3, V4 and V5. Now to prove graphs are isomorphic, what you have to do? You have to construct a function f. Function f from this set u1, u2, u3, u4, u5, and another set is v1, v2, v3, v4, v5. How should be the function? Function must be bijective, and for the second condition, whenever there is edge here between u and v, there must be edge between fu and fe. So you have to construct such function. How will you construct such function? See properly. You understood the meaning of isomorphic, that is both the graphs are almost, we'll say, identical graph. So whatever properties this graph has got, all properties must be there with this graph. So simple thing again, this is just simple logic which you can understand otherwise also. But you can see here u1 is the vertex whose degree is 1. And here v5 is the vertex whose degree is 1. So obviously we must have v of u1 is v5. And this way you have to construct the function. Now here u2 is the vertex, it's the only vertex whose degree is 3. Here v3 is the only vertex whose degree is 3. So obviously we must have f of u2 is v3. And now you can think of rest all. See, here u2 is same as v3. u2 is adjacent to u3 and u5. And v3 is adjacent to v2 and v4. And that tells me I should have fu3 is v2 and fu5 is v4. And what is left with us is fu4 will be v1. This is just randomly we found out depending on degrees, depending on the adjacency, and now you need to cross check, is it isomorphism? Isomorphism means the function by which the graphs are isomorphic, and you can cross check the condition. u1, u2 is an edge, yes. So V5, V3 is also an edge. Then U2, U3. Here V3, V2. Like that you can check for all. And you will see G and G dash are isomorphic. And when G and G dash are isomorphic, we denote it in this way. G is, how to read it? G is isomorphic to G dash. That is the clear meaning of isomorphic graph. And when you are asked, show that the graphs are isomorphic, you have to construct function which satisfies this. And if you want to show the graphs are not isomorphic, at this stage I won't tell you, you will come to know slowly as more and more properties of graphs you will study. When the graphs are not isomorphic, what you have to do, you have to see some property which is satisfied by this graph and not satisfied by this graph. For example, next we will study what is connected graph. So you may have one is connected, other is not connected, then the graphs are not isomorphic. Or here, whatever you have studied up to this, you can see here there is one vertex of degree 1. And if you have here two vertices of degree 1, or if you have no vertex of degree 1, again we will say the graphs are not isomorphic. So to prove not isomorphic, you have to pick up some property which is satisfied for one graph and doesn't other graph doesn't satisfy it. And to prove they are isomorphic, you have to construct a function. The function should be bijective function on vertices. Function should be bijective. Moreover, it should satisfy the second condition. Whenever UV is an edge here, FUF is also an edge over here. And this way you can prove or disprove whether the graphs are isomorphic or not. Just go through, then we will prove one more result for isomorphism. Now, the next result we are going to prove. For that, I just have to tell you what is the meaning of complement of a graph. Again, first I will tell you, then I will define. If this is a given graph, A, B, C, D, 4 vertices. Now just think on 4 vertices, what would be the complete graph? This is a complete graph on 4 vertices. These are all possible edges. So complement means if this is your G, your vertex set remains same. Complement means whatever edges are not here, that I am going to take over here. Consider this complete graph. From this complete graph, here we have only these 4 edges. So what are not there? These 2 are not there. Then these 2 are not there. Now I will have a graph with these 2 edges, and that is called as complement of G. G complement. Now you think, how will I define G complement? I gave you the meaning. How to define it? We can define it in this way. When I have to define any graph, first thing we have to define vertex set and then you have to define the edge set. So first I will have, let G be a given graph, then complement of G, that is either G complement or G dash, is a graph where we have to define vertex set as well as edge set. So first I have vertex set of G dash. You can see it is same as vertex set of G. And now to define edge, what we have to do? UV belongs to edge set of G implies FUFV, I'm sorry, UV does not belong to edge set of G dash, and other way also. And now you can understand simple meaning. Whenever the edge is here, it is not here, and whenever the edge is here, it is not here, and that is the complement graph. So I hope this meaning is clear, and now we are going to prove one small result. The result says if two graphs are isomorphic, then their complements are also isomorphic. and even the converse is true. So I will set a theorem and let's prove it. So I have here G and use the notations. G is isomorphic to H if and only if G dash is isomorphic to H dash. Means if two graphs are isomorphic, their complements are isomorphic. If complements are isomorphic, the given graphs are also isomorphic. Let's prove it now. Now first we'll prove this way. Means what we have to prove? G isomorphic to H, to prove G isomorphic to H implies G dash is isomorphic to H dash. Okay, how to prove it? First, when I want to prove G dash is isomorphic to H dash, first thing we should have a function which is a vertex set of G dash and vertex set of H dash, and the function is bijective. Now, vertex set of G dash and H dash is same as vertex set of G and H, and these are isomorphic. So obviously we have such function. So what I will have, G isomorphic to H implies there exists F from vertex set of G to vertex set of H such that F is bijective. And I will say this gives me there exists F from vertex set of G dash to vertex set of H dash such that F is bijective. What is the reason for this? Since vertex set of G is same as vertex set of G dash and vertex set of H is same as vertex set of H dash. So first part we proved there is a bijective function from the vertex set. But the second one we want to prove what's the definition of isomorphism. When we say G is isomorphic to H, that whenever UV belongs to age set of G, we have to prove FUFV belongs to age set of H. That is what we want to prove. Means here we want to prove if any age UV is in G dash, then FUFV is an age for H dash. How we will prove it? Just pay attention now. Again, it's very simple. I will have, first of all, now what we have, G is isomorphic to H. So will have it here. Since G is isomorphic to H, what that implies is UV is age here implies UV, FUFV is an age in H. Okay, so let's continue here. This gives me, as a second condition we are trying to prove, UV belongs to age set of G, that gives us FUFV belongs to age set of H. See properly, these are isomorphic. F is an isomorphism. So any age UV here means FUFV is here. Now UV is in age set of G. So it's the common sense that gives me UV is not in the age set of G dash. Are you getting this point? What were the isomorphisms? G dash and H dash we want to prove they are isomorphic. So we want to prove whenever UV is here, FUFV is here, and for that you have to understand this part. Whenever UV is in EG, UV is not in EG dash. Or if UV is in EG dash, that gives me UV is not in EG. So UV is in G dash means it is not in G. It is not in G means FUFV is not in H, and that means FUFV is in H dash. I will write this so you can understand clearly. So before I write, again understand what I want to prove. What we need to prove? We need to prove whenever UV is in G dash, FUFV is in E of H dash. I will first write what you want to prove so you can understand it very well. We have to prove UV belongs to age set of G dash implies FUFV belongs to H set of H dash. Am I right? This is what we want to prove. Then we can prove G dash and H dash are isomorphic. Now clearly UV belongs to H set of G dash. That gives us UV does not belongs to H set of G. Why? Because G and G dash are complements. Now UV does not belongs to EG. That means FV does not belongs to H set of H. Why? Since F is an isomorphism from G to H. F is a function which is isomorphism from G to H. So, if UV doesn't belongs to G, FUFV also doesn't belongs to H, and FUFV does not belongs to H, that gives me this FUFV belongs to H set of H dash. So, we have proved whenever UV is an H set of G dash, FUFV is an H set of H dash. But to prove isomorphism, see the condition is if and only if UV belongs to EG implies and implied by FUFV belongs to E of H. It is both the ways. So reverse way, you can just cross check these steps. FUFV any H is an H dash, means that H is not in H, means its pre-image is not in G, and that means it is in G dash, and so we are getting G dash is isomorphic to H dash. So what we have proved, G is isomorphic to H implies G dash is isomorphic to H dash. You have to prove reverse way. To prove reverse way, don't you think it is just easy to prove complement of complement is the same set? If I prove G dash dash is G, automatically it gives us the reverse result. This complement is this complement is this. So these two are isomorphic, implies their complements are also isomorphic. And how will you prove G dash is G? You can do it. I'm leaving this for you. It's very simple. G dash is always G, because what is dash? Whatever, if any age is not in G, that will be in G dash. Any age not in G dash, that will be in G. Using this, you can prove this result, and from that you can get reverse way also. So just go through this proof and try to understand just for a few minutes. So I hope you understood this. So we'll stop here for this isomorphism, and next lecture, our next video, that will be for the next property of graph, what is called as connectedness. So next video we are going to see what is connected and disconnected graph. Thank you very much.